Hello, welcome to another lesson. So today we'll be continuing on with the 3D trig lesson, where last lesson we introduced the framework for 3D trig, which comprises of three sort of fairly straightforward and fairly predictable steps. That framework basically can be applied to most questions. Now, not all questions can be done using that framework. Obviously, there are some harder ones which we'll explore in the next lesson. So today, the aim is to basically apply that framework to a number of past paper questions. So without further ado, let's hit up some of these past paper questions. So the first past paper I have is from 4th Street, where you can see that a number of these past paper questions apply the 3D trig questions with the context, right? And a lot of contexts are quite wordy, so that can present itself to be quite difficult for a lot of students, especially where, not in this question per se, but in the ones after where there's bearings involved, right? So to help sort of break this question down, let's comb through these words and sort of extract out the math. So from a point C, vertical cliff. So a lot of the times they talk about something, an object that's vertical, or an object or something that's vertical. In this case, it's a cliff. Sometimes it's a flagpole, a tower, mountains, etc., etc. So you got to assume, if it's vertical in the diagram, assume some sort of right-angled elevation with respect to these 2 points on the ground. Yeah. So let's see. So 200 meters high. Yep, got that. Two ships P and Q. Yep, got that. Are reserved at sea level. A is the foot of the cliff, got that. P is due south. And the angle of elevation of C is 45 degrees from this point P, which is due south. Q is 50 degrees west and has an angle elevation of 60. Okay, so this question is actually made easier because they gave you the diagram, right? But it's interesting here that they gave you that P is due south and Q is 50 degrees of south, 50 degrees west. So both of these coordinates, that's due south and this guy is south, 50 degrees west. The whole point of that is to give you this 50 degrees. Right? The fact that they gave you that in the diagram makes your job a lot easier, because with that 50 degree in place, we can just apply our usual 3-step process with the 2 triangles using SOHCAHTOA and then the base to connect the 3. Now, what are we actually finding? Find the distance of PQ. So this distance here. Perfect. Let's apply the framework as we always do. So right. So steps 1 and 2 is basically the 2 right-angled triangles, which helps us get expressions to help us then find PQ on the base. So this is the first triangle there, 60 degrees elevation and 45 degrees elevation. And both of these have a common 200 meters as this side here. Now, so a smart thing to do, if they don't give it to you in the diagram, introduce your unknown variables. So technically speaking, I can use the signs that are given, like QA here and C and P here. I can, but for my purpose, I'm just going to introduce A and B just to make my life a little bit easier. Now, in this triangle here, you get tan 60 degrees, which equals to 200 on A, making A the subject, 200 on tan 60. Similarly, in this case, tan 45 degrees equals to 200 on B. Switch those around. B is 200 on tan 45 degrees. Now, in this question, it's actually quite nice because they use nice exact values, right? Yeah, 60 degrees and 45 degrees. So let's actually put them in. So I know that tan 60 is √3, and I know that tan 45 is 1. So what that means is it's quite nice, because then you get like 200 on √3 as your value for A, right? Give that a nice blue highlighter there. And for B, that's 200 on 1, which is 200. Put a box around that. So give that a highlighter, green. Yep. So step A, step 1 and step 2, classic. And then step 3, once again, falls into the framework, right? Where we have a triangle on the base that's 50 degrees here. PQ is missing, and we have the two sides we basically found values of A and B there. And then we just use the cosine rule, right? Where this side is a missing side. So cosine rule basically says PQ squared equals to A squared plus B squared minus 2AB cos of the angle in between. So one of the hardest things for a lot of people is getting that 50 degrees if it's not given in the diagram. And the next question, we'll actually see an example from Sydney Grammar, which touches on that point there. So the values of A and the values of B, I would sub into here. So basically this guy here, I'm going to sub that into A and B. This 200 value here into B and B. And then quite simply, it becomes a calculated exercise thereafter. So that's 200 on root 3 squared plus 200 squared minus 2 times 200 on root 3 times 200 times cos 50. So punch that in and make sure you remember to square root that. Yep, now what's the question say to round off? Nearest meter. So if you punch out in the calculator, should be like 153.7-ish, so 154 meters. Is that okay? So basically, for this fourth street question, it's very typical, falls under the framework. The harder thing here is if they don't give you the diagram, that's going to be quite challenging. But in this case, everything's quite stock standard, but with a bit of context in terms of the 3D trig diagram. Let's look at now a question from Sydney Grammar. So a little bit more wordy and verbose, but let's have a look. So I have here a context where AB, which represents Abby and Bobby, are bushwalking on flat ground. They can see both. They can both see the mountain range. So once again, here we have a mountain range. So the context for the vertical is a mountain range, while before, what was before? Was it a cliff? Was it? Yep, vertical cliff. Sometimes you see a flagpole. Sometimes you see a tower, etc. Same thing. 200 meters is given. From Abby's position A, the bearing is now. Bearing is 35. So I'm going to highlight that in green because that's not given in the diagram. In fact, the whole purpose of that is basically to find the angle, right, in between here that's currently missing, right? That's the biggest purpose of having the bearings in there. Yeah. Let's have a look. So from A, I got that. I'll highlight that. I'll draw a diagram to get that later. And angle of elevation of 18 degrees. Perfect. Got that. Right. From Bob's position, B, mountain bearing of 330 degrees true and elevation of 15 degrees. Perfect. Let the base top be XY. Okay, cool. Now, step 1, prove that angle AXB. I want this to be 60 degrees. That's what it's telling me to prove, right? And then find the distance of AB, right? So part B, question mark, right? Maybe call that X. That's part B, distance. All right, so that's my question. So the only main difference between this question and the one from 4th Street previously is that I need to now prove that the base angle here is 60 degrees. Yeah, so what I'm going to do, I'm going to do a bird's eye view diagram for part 1, where we have point A looking up to point X, looking down to point B. Now, I don't really mind how long these lengths are at the moment, right? Now, what I need to do is basically to use bearings to get an angle for this guy, right? I need to prove that this guy here is 60 degrees. So, step 1, if I draw one of these north, east, south, west cross arrows, right, in here, I've got the first fact that the bearing of the mountain from A is 35 degrees. So from here to here, right, this line here, this angle here has a bearing, oops, of 35 degrees, right? Easy. Yep. So that takes care of this bearing here, tick. What else do I know? That the bearing of the mountain from B, so once again, I'm going to draw an arrowhead at B, right, where both of these have what, pointing to true north, and it's telling me that the bearing from B to X is 335 degrees. So what that means as an angle, if I swing around here, that is 335 degrees, which basically means that this angle here, right, is 360 minus that, which is 25 degrees. Now, both of these should give me enough information if I was to draw an arrowhead at X using, can you see alternate angles, right? 1, 2, 3. I can actually say that that's 35. This must be 35 degrees as well. Similarly, using alternate angles at B, I get this angle here to be 25 degrees, right? So from observation, right, which is the way to tell your teacher to look at your diagram and look at your working out, angle AXB is 35 plus 25 degrees, which is 60 degrees. Tick. Yep, all good. So I'll give that a highlight as my answer. So once you do that, that allows you now to use the framework to find the answer. So that was just a long-winded way of finding the angle to be 60 degrees. Now, if this was an exam and you couldn't do part 1, it's only worth 1 mark. Use it to do part 2, right? Don't be silly and leave out everything. So now let's apply our framework. Our framework is what it always was, right? We got one right angle triangle. The second one sort of points backwards, not that it matters which way you do it, right? Points backwards. So now I know they got AX and all that. I'm gonna, in the diagram here, introduce the letter A there and introduce the letter B there, just to make my working out a bit easier. So let's start with the triangle AXY, where I know how high is that? 200 meters. I think the last question was 200 meters as well. 200 meters there, right? The angle of elevation there is 18 degrees. The same is true for the second triangle, where this angle of elevation here is 15 degrees. And then all I got to do, put in A, put in B, and use SOHCAHTOA to do this, yeah? Which is always, in this case, 10. Now, before I finish this question off and use the same framework, I'm just going to do one subtle difference. So tan equals to 200 on A. Because if you look at this, right, A equals to 200 on tan 18 degrees. Now, I'm not a big fan of having tan. I think I said this in the last video, in the last question. Not a fan of having tan on the bottom, right? This bit here. Yeah, it's not nice to punch in the calculator. So if you were smart about it, instead, what you can do is use this angle over here, where I know if this is already 90 and this is 18, these two must add up to 90 degrees. This must be 72 degrees. Similarly, if this was 15, this must be 75 degrees. If you use this angle instead, where tan 72 degrees is opposite on adjacent, when you make A the subject, you just get a nicer expression of 200 tan 75, where it's no longer a fraction, right? Just makes your life a little bit easier. Similarly, right, you can use tan of 15 equals to 200 on B, and then go, well, B equals to 200 over, sorry, I'm running out of vertical space. Let me just rub that off, make it a bit neater. Tan 15, right? That's all good. However, once again, right, tan is on the bottom, not ideal. So instead, let's use the 75 degrees, where tan 75 equals to B on 200. Yeah, and B equals to 200 tan 75 degrees. It's just cleaner, right? It's just cleaner. So once you do that, we have now, I'm just going to shift everything up so I can actually use the vertical space. I can use the triangle now with 60 degrees to basically connect my answers together. Can I ask a favor? You know what? I'm just gonna move these solutions around a little bit so I can have a bit more vertical space to do my thing. All right. So let's quickly whip up a diagram of the base so we can visualize it, right? So I know this is 60 degrees now, and I know this is A and this is B, right? And this is AB, right? You can call it X, you can call it AB, but so cosine rule, A squared, B squared minus 2AB cos 60 now, right? So this is all easy, sub in A and B, just like I did before. I won't highlight it because we know what we're doing. So equals to, now, no fractions, which is nice. So tan 72 degrees squared plus 200 tan 75 squared minus 2 times A B cos 60. And then you punch it in the calculator and ensure that you square root it to get the answer. Now the question says nearest meter. So if you do that correctly, I believe it's about 690 point something, so 690 meters. Is that cool? So once again, right, the framework works, right? And it works with so many questions that look like this. In this case, the hardest piece is that bearings part 1. So once you draw it from a bird's eye view and you basically use some alternate angles, you get the 60 degrees. But even if you couldn't do 60 and this was an exam, use part 1. If you just lose part 1's mark of 1 mark and then use it for part 2, right? Quite straightforward. All right, now let's do one more question just to end this session. It's a question from Sydney Girls. Part 1 fits the framework, and then part 2 has a little bit more and can easily students can lose marks for it. So from Sydney Girls, 2014. So once again, there's a bit of context. Let's see. So in this one, let's have a look. So additional to what we normally do, there's a footpath on the horizontal. So the footpath has 2 parallel edges. So footpath, that and that is a footpath, right? Yep. So like a road on the floor. See these horizontal, like we always get, right? With H meters, okay, yes, yes, yes. With its base on C, one edge, and A and B are 2 points, where you're given that AB is 7 meters, right? So in this one, it looks like we're going backwards, where instead of giving you the height and finding the distance between them, they've given the distance, and now we got to find the height, where ACB is 60 degrees. So they gave you the angle in between as well. Beautiful, right? Angle of elevation of 60 and 30, 60 and 30. Okay, everything's framework right now, right? No surprises. Find the height of the flagpole. So find H. Find the exact width of the footpath is where a lot of people here. So find the exact height. Okay, cool. I've got to find that. Exact width of the footpath. So you can imagine if this was a footpath, I need to find the distance from here to here. Now, I believe in the solutions, it says a lot of students, when they did this test, accidentally or inadvertently simplified the question and assumed that this distance here for BC was the width of the footpath, which is obviously incorrect. It makes a right angle though, right? And we'll deal with that later, right? So that's for part B. So part A, let's fit the framework, get the 3 marks. And then part 2, let's work a little bit more to get the 2 marks thereafter. So part 1, very simple, right? Very straightforward framework question, right? Where DCA looks like that. And then there is another right angle triangle where it's DCB. This is H and this is H. 7 meters, 7 meters. And what's my angles? 30 degrees. And 60 degrees. Nice exact values, right? Keep that in mind, right? So these angles here, nice and exact. Now, so once again, as discussed in the last question, smart idea, use these angles upstairs, right? It just makes for easier exact values, right? So let's have a look. Actually, for this one, it literally doesn't matter because the exact values are there. So, you know what? I won't use the green because I'm going to be subbing in the exact value. So the expression is easy anyway. So tan 30 degrees equals to h on 7. Now, tan 30 is 1 on root 3, as you guys would most likely know. Therefore, h equals to times the 7 up, 7 on root 3. Right? So we didn't need to use that green angle because it would have given us a very similar expression as well. So tan 60 is equal to h on 7 times the 7 up. I've done that wrong. Yeah, I've done that wrong. Let's see, times the 7 up. Oh, no, I haven't. I haven't actually. Tan 60, sorry, I'm just making sure. Yep. So h equals to 7 tan 60. Ooh, I've done this completely wrong. Yeah, completely wrong. That 7 should not be there. Yeah, I was thinking those fractions look too nice. I've yet to introduce my a and b. Yeah, which is actually what I wanted to do. A and b. How silly of me. Let's fix that. A and b, right? So it's not 7 at all. Yeah, I'm not actually making h the subject. I thought that was kind of weird. I thought that was kind of nice, but a bit too nice, right? So let's fix that. Rectify that situation, please. So it's actually h on a, and I'm actually trying to make a the subject, my friends. A equals to root 3h. That's better. Tan 60 is h on b. Yeah, let's fix this expression here. Yep. Spelt funny when it wasn't a fraction when I was using black. So b equals to h on tan 60. Therefore, now tan 60 is root 3, so that's b equals to h on root 3. That's better. Much better, right? So got A, got B. On the base, so we have a triangle which sort of looks like that. Now we have the 7 in there. So the sides are A, B, and C. And we introduced A and B into here. And also on the diagram is given that this is 60 degrees. Perfect. Right? So therefore, if we use the cosine rule here, I got sorry, I'm just going to scroll down a bit. Now, in this question, because we're finding the height, right? Make no mistake, when I sub all the height values into the cosine rule, I should be able to make h squared the subject and then find h, right? So let's have a look. So 7 squared equals to a squared plus b squared minus 2ab cos 60, right? So let me highlight this in green, sub that into a and b. Highlight this in blue, sub that into B and B. So just to be absolutely clear, this is coming in here and coming in here, while the blue is coming there and there, right? So that's 49 equals to a squared plus h on root 3 squared minus 2a b. Well, that's nice. Root 3's cancel out. Cos 60. Now, cos 60, once again, nice exact value. Cos 60 is half, isn't it? So it looks like a very nice, all these whole numbers here, right? Because you get 49. Now, before I do anything, can you see h squared, h squared, h squared? I can factorize h squared out from all terms on the right-hand side, right? That gives me a nice bracket where root 3 squared is 3 plus 1 on root 3 minus root 3's cancel out. So that's just 2 times half. That's just 1. Oh, that's a nice expression, right? Where if you made h a subject, I believe, and then square rooted it, let's see, I believe you get root 21. I think the question is asking for exact value, is that right? Exact height. So let's leave that as that. Yep. So the framework works, right? The framework is as what it is, hasn't changed now. So part 1, classic 3 marker. Now part 2, let's have a look. I'll copy this diagram into the next worksheet just so I can have a bit more space. Now, in this question, so like I drew in the last slide, we have the width of this footpath, right, looking like that, where from the previous part we found this line already. So it looks like I'm going to use a bit of Sokotoa. Let's actually draw the whole base out again to make it look like this, right? So the solutions basically for this question indicated that a lot of students at Sydney Girls, when they looked at this question, they interpreted the line CB as the sort of height, also the width of the footpath, which is obviously incorrect because it's a diagonal length, right? So we need this side, right? This is the side that's missing. Let's call that maybe X. That's the side we want. So there's a couple of ways to do this, right? Interestingly, in the solutions, I use area of a triangle to basically do this. I'm just going to use our classic sine rule and cosine rule, etc., to do this. So now, from our part A, or part 1 rather, we found these two sides. That's A and that's B, right? And the bottom side here is 7 meters, right? So B, from memory was, well, not from memory, my memory's poor, H on root. So this is H on root 3. Now we found H actually, so maybe we sub that in. That's like root 21 on root 3, which looks to be root 7. Yeah, and A, so maybe I'll do A down here, was, I believe it was root 3H. So that's root 3 times root 21. Now that's like 3 root 7. Yeah. So root 7, 3 root 7, right? Now what I'm going to do then, let's see if this works, right? Sorry, I just got some working out here just so I don't do any boo-boos. Let me make sure we're doing this right. So that's, yep, that looks fine. Looks fine, I think. And which one's my A and B? B's down here. Ooh, I've got this the other way around. Okay, my apologies. So A is actually this side here. So I'm just gonna switch these answers the other way around, right? So in my diagram, I actually called this B and this A. So A is root 3H, which is 3 root 7, and B is H on root 3, which is root 21 on root 3, which is root 7. Just so we can get that correct. Now, so using your cosine rule or sine rule, I want to find this angle here. Now, why do I want this one? Because once I find this one, right, I can get this angle here using supplementary angles. Yeah, call that theta, alpha if you want to. You actually don't need to, and I'll explain why in a sec. I'm just going to leave this here as 180 minus theta. Right? Maybe I'll draw it better. 180 minus theta. That's better because when you think when you use a sine rule and get an expression for sine, I'm probably going to use Sokotoa here, which is also sine 180 minus theta. For those that know their all stations are central well, that's just sine theta, right? Piece of cake. So here's the game plan. In triangle ABC, I'm going to use the sine rule, yeah, where the matching pairs are going to be these two and these two. Using sine rule, I can find an expression for sine alpha, so sine theta. Using that sine theta, I'm going to use Sokotoa in the other triangle, maybe I'll call it the green one, right? And then find myself the value of x. So let's do this. So let me just draw out everything a bit neater so I can actually get you to visualize it. So this side's 7 and this side's 3 root 7. So using sine rule, I got sine theta over its matching side, 3 root 7, equals to sine 60 over 7. Now, we know that sine 60 is root 3 on 2, so sine theta equals to 3 root 7 equals to root 3 on 2 over 7. So I'm going to do two things. Firstly, the 7 and the 2 can be multiplied, right? Because it's on the bottom, so that's 14. And multiply this guy up. Yep. See where that takes me. So sine theta equals to, what's that, 3 root 21 on 14. Let me just check that. Perfect. I'm going to leave it there, right, as an expression. Can't really do anything more with that. Now, once you have that for sine theta, I'm going to now draw this green triangle over here, making it look like right angle triangle. The side that's missing is X. That's the width of the footpath. That's what I want. I've got this side here as B, right, which is root 7 as per the diagram here. And this angle here is 180 minus theta. Now, using my SOHCAHTOA, I've got sine 180 minus theta equals to opposite on hypotenuse. But I know using my all-station central, right, sine 180 minus theta is in the second quadrant and sine is positive there, so that's the same as sine theta. Is that all right? Which is nice because I have the value of sine theta over here, and I'm just going to plug this guy into this value here. Pretty straightforward. So let's have a look. 3 root 21 on 14 equals to x on root 7. Right, then it's a simple case of timesing the root 7 up. What's that? Root 7 times the 21, split that up. It'll be root 7, it'll be 21 root 3 on 14. And that looks like it simplifies to, what's that? 3 root 3 on 2 meters exactly, which is the width of the footpath. So this question here for part 2, basically just flows on from our classic 3D trig question and framework. Once again, the hardest thing about here is not part 1, it's part 2 where you have to do a bit more, but hopefully that wasn't too bad. It was just, I like this question also because it's got nice exact values just so you can actually get numbers in play instead of just punching into your calculator. So I'm gonna leave this lesson there. Hopefully it was useful, and if you like this video, please share it with your friends. Give me a like and maybe give me a few subscribes. Next lesson, we're gonna basically try to do harder 3D trig questions, which sort of falls outside of the framework, or the context and the words and the bearings part is quite hard. So until then, I'll see you later.